Okay, so sorry, my 4-year-old came into the room at the end of that last video, needed something, so I had to cut that one short. Sorry about that. I went ahead and finished this example almost. There's one little part that's missing, but we had already established that the antiderivative for e to the x is for e to the x. And I had started talking about this guy right here, this quotient. If I had asked you to take the derivative of that quotient, you wouldn't just take the derivative of the numerator and denominator separately. You know better than that now. The derivative of this would require the quotient rule. Now, we don't have an antiderivative counterpart to the quotient rule. In fact, we're not even going to come up with one because you'll see in Calculus 2, actually, we don't need one. But rather than try and take the antiderivative of this thing as written, it's better to try and simplify it first. You see, 5x cubed over x squared is 5x after simplifying. The square root of x, or x to the 1/2 power over x squared, is x to the -3/2 power. And by rewriting this in this form, I can just apply the antiderivative counterpart to the power rule for each of these. Okay? So now that I've established that, what is the antiderivative of 5x? Well, x to the 1st power, if I add 1 to its exponent, that becomes a 2, and then I have to divide by that same number, 2. It becomes 5/2 x squared. Take the derivative of this to see that 5x is what you get as a result. Same thing here. Add 1 to the exponent, which would give me -1/2, and then divide by that exponent, -1/2. And actually, I did that wrong. That should be +2 there, not... Make that a 2, not 1/2. Because if you divide by 1/2, it's the same as multiplying by 2. The only thing that I'm missing here is my plus c, so I need to include that. Okay, but hopefully that gives you an idea of how you're thinking through these antiderivatives. Let's take a look at another example. Let's suppose we're looking for f of x, where f prime is equal to this function, 2 sine of x plus 5 times 1 plus x squared to the -1 power. That plus is not supposed to be there. And then we're also given this additional information, f of 0 equals 3. We'll talk about why this is important in a minute. But let's start with this guy. I want little f of x if f prime is equal to this. In other words, I'm looking for an antiderivative of this. Well, starting with this guy right here, f of x has to be equal to, what is the antiderivative of sine of x? It's negative cosine of x. The derivative of sine is cosine of x, but the antiderivative would be negative cosine. So this becomes -2 cosine of x. Now this guy right here is the same thing as 5 over 1 plus x squared. And 1 over 1 plus x squared is the derivative of the inverse tangent function. So the antiderivative of this would be the inverse tangent function. So from that, the antiderivative will look like 5 times the inverse tangent of x. And then I'm supposed to have this plus c here. Okay, now notice it did not say find all functions f of x like my previous example did for g of x. And it doesn't say find the most general antiderivative. It just says find f of x, implying that there's only one function. And the reason for that is because I have additional information here that I haven't used yet. It says f of 0 is equal to 3. Plugging 0 into my function, this guy, setting it equal to 3, which will go here, is going to allow me to solve for that unknown constant c. So I'm going to do that. 3 is equal to -2 cosine of 0 plus 5 times the inverse tangent of 0 plus c. Now cosine of 0 is equal to 1 times -2. That would equal -2. Inverse tangent of 0 is 0. That term goes away. So I'm just left with plus c. Adding a 2 to both sides gives me c equals 5. So the function that I'm looking at, f of x, is this, -2 cosine of x plus 5 inverse tangent of x plus 5. Notice now I have a specific function where that constant is known. It's not just some arbitrary constant c. Okay? All right, next example. A particle has an acceleration a of t equals t squared minus 4t plus 6 I'm going to say that this is in meters per second squared at time t. We're asked to find the position of the particle s of t, so we're actually looking for the position function. And now we're given two conditions, s of 0 equals 0, s of 1 equals 20. How do you do this? Well, here's what I know. V prime of t is equal to a of t, where v is the velocity function. So what this means is that if acceleration is the derivative of velocity, then velocity is the antiderivative of acceleration. In addition to that, I know that s prime of t is equal to v of t. The derivative of position is velocity. So the position function is the antiderivative of velocity. What this means is I need to take an antiderivative of my acceleration function to get my velocity, and then take an antiderivative of that to get my position function. So let's do that. V of t is equal to what? I need an antiderivative of this guy. That's going to be 1/3 t cubed. If you use the formula for the antiderivative directly, it's going to look like t cubed over 3. I tend to prefer to write that as 1/3 t cubed. That's just my preference. Here, adding 1 to t would be 2, and then dividing by 2 is going to be 4 divided by 2, which is 2. 2t squared plus 6t. Notice the constant picks up a factor of t. And verify that this is correct by taking the derivative of 6t. It's 6. That's what we're expecting to get. Plus some arbitrary constant. I can't solve for this constant yet because I don't have any of these conditions involving a v. They both involve s. I don't know what to plug into v and what that's supposed to equal. So I'm going to leave the c alone and then just take another derivative. S of t. If I take the antiderivative, not derivative, if I take the antiderivative of this, I'm going to get t to the 4th. Then dividing by 4 gives me 1/3 divided by 4, which is 1/12. Verify, take the derivative of this, see that we get this. Antiderivative of this guy is going to be minus 2/3 t squared, cubed, sorry, not squared. Verify this, take the derivative, make sure we're getting that term. This is going to become plus 3t squared. Again, verify, take the derivative of this to get that. Plus, this is a constant. Remember the last time we had a constant, its antiderivative was just that constant times t. So this is going to become plus ct. But there needs to be another arbitrary constant tacked onto this thing. So now I have two constants that I have to worry about. Okay, how do I figure out what those are equal to? Well, now I just use these two conditions that are given to me in the statement of the problem. S of 0 equals 0. So if I plug a 0 into both sides of this thing, I should get a 0 as my output. Plugging the 0 in on this side, every term with a t in it is going to go to 0, leaving me with d. So d is equal to 0. That's easy enough. Now I'm going to plug a 1 into both sides and set that equal to 20. Plugging a 1 in for t gives me 1/12 minus 2/3 plus 3 plus, what did I say? I'm plugging a 1 in, so that would be plus c. Okay? Let's see. I'm going to get a common denominator, so 12 is my common denominator. 20 times 12 would be 240 over 12 on that side. And then over here, I'm going to have 1/12 minus 8/12 plus 36/12 plus c. That's going to give me 240 over 12 equals what? 1 minus 8 plus 36. That's 29/12 over there plus c, which implies that c is equal to, I have to subtract 29/12 from both sides, which would give me 211/12. Okay? That is just going to become c. We already said that d is equal to 0. And so this means that s of t equals 1/12 t to the 4th minus 2/3 t cubed plus 3t squared plus 211/12 t. I'm not going to write plus 0. There's no point. So that's the function that I'm looking for. Okay? Awesome. All right. Last example, then we're going to wrap up chapter 4. The graph of a function f is shown below. which graph is the antiderivative of f? Now, we've done similar problems where we're given a function and then given other graphs and we're trying to match which of those graphs is the derivative of that function. And we use our knowledge of those functions. You know, we know how increasing and decreasing relates to the derivative and stuff like that. So let's take a look at our function f. We're looking for an antiderivative of f, which means we're looking for which of these curves has f as a derivative. Now, if you notice, the function f is positive up until we get to this point right here, at which point it's negative. So if that's a derivative of the function that we're looking for, then we're looking for a function that increases up to this value and then hits a relative maximum and then decreases away from it. A appears to do that. Notice that the function a, or the function indicated by a here, increases, gets to this point where there appears to be a horizontal tangent, and then it decreases away. Do any of the other functions do that? B doesn't. B is decreasing to that point and then increasing away from it. It's doing the opposite. And C appears to be increasing the entire time. So B and C are definitely not going to be antiderivatives of f. The answer has to be A if it's going to be one of those three. Okay, so again, that's kind of like thinking in terms of the derivative, but now the function that we're given is the derivative, and we're not trying to match it to its derivative. Okay, that should do it for section 4.9.